Economics, business, insurance, mathematics, auto racing, the list goes on, are all fields in which analysts use mathematical modeling to maximize profits or production or minimize costs. Hi, my name is Tom Atwater, and that's what we'll be doing in today's lesson, applying the first derivative to solve maximum and minimum problems in real-world applications. Let's look at a strategy for solving these types of problems. Strategy for solving max-minimum problems. First, obviously, read the problem carefully. Identify the information you need to solve the problem so that you can clearly understand the problem. Number two, develop a mathematical model of the problem. Draw pictures, label the parts that are important to the problem, introduce a variable to represent the quantity to be maximized or minimized. Using that variable, write a function whose extreme value gives the information sought. 3, graph the function. Find the domain of the function. Determine what values of the variable make sense in the problem. Number 4, identify the critical points and endpoints. Find where the derivative is 0 or where it fails to exist. 5, solve the mathematical model. If you're unsure of the result, support or confirm your solution with some other method. Interpret the solution. In other words, translate your mathematical results into the problem setting and decide whether that result makes sense. Let's look at an example where we apply this method to solving a real-world example. Minimizing perimeter. What is the smallest possible perimeter for a rectangle whose area is 16 inches squared? And what are its dimensions? Okay, so what we know is the area is equal to 16. And the area of a rectangle is length times width. So we start off with area equals length times width, which equals 16. And therefore, in this, I can solve for L and say that L is equal to 16 divided by W. Now let's go to perimeter. The perimeter, which is what we're trying to minimize, is equal to 2 times the sum of L plus W. What we need to do, though, of course, is replace or substitute the 16 divided by W for L so that we have this P in terms of just one variable, in this case W. So P would be equal to 2 times 16 over W plus W. And that would be equal to 32 over W plus 2W. And now what we need to do is take, because we want to find the maximum, or I'm sorry, the minimum perimeter, what we want to do is find the first derivative, because that's what allows us to find either a max or a min. So we take the first derivative of this. P prime is going to be equal to. Off to the side here, I want to point out that this is really 32 times 1 over W. And 1 over W is just like 1 over X. And we've seen that many times. So we know that the derivative of it is negative 1 over W squared. So it's going to be, in this case, negative 32 over W squared. And then plus 2, because that's the derivative of 2W. Now, we need to set this equal to 0. And then solve that for W. When we work out the mathematics of this, we will get that W is equal to plus or minus 4. But of course, I'm sorry, yeah, but of course we don't deal with the minus because you can't have a width of negative 4. So if W is 4, then we can calculate L, remember, because we said L is equal to 16 over W. So we get that L is equal to 4. Well, what that tells us is that it's actually, the perimeter is 16, and it's really a 4 by 4 rectangle, i.e., it's a square. So that's our answer. Let's try another problem. Let's take finding an angle. We have two sides of a triangle which have length A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? And the formula we're going to use for this is the hint. Area is equal to 1/2 times A times B times sine of theta. So what we're going to do is write down the area, which is 1/2 AB sine theta. And what we're trying to do here is maximize the area. So we take the derivative, the dA d theta. So we're taking the derivative of the area with respect to theta. Well, all of these are constants. A is the side of the triangle, B is the side of the triangle. So those remain as is. And now the derivative of sine theta is cosine theta. We set this equal to 0 because we want to find the critical point, the point at which it's either a max or a min. In this case, we're looking for a max. But what we know is this will be 0 when cosine theta is 0. And the angle whose cosine is 0 is pi over 2. And what that tells me then is that it's a 90-degree angle. Oh, 90-degree angle means that it's a right triangle that will maximize the area given a triangle. It's got to be a right triangle. Let's carry these ideas even further and do an example from business. We're going to design a poster, and what you know is this. You're designing a rectangular-shaped poster to contain 50 square inches of printing with a 4-inch margin at the top and a 2-inch margin, I'm sorry, at the top and bottom, the 4 inches, and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? I think it's best here if I draw a picture to help describe what we're trying to do. We've got the inside writing area of the poster. And so we have L and W. But now what we know is that we have to have a 4-inch margin on the top, a 4-inch margin on the bottom, a 2-inch margin on each side. And so the overall poster would look like this. And I know that the width is actually going to be W plus 2 or W plus 4. And I know that the length would be plus 4, so L plus 8. What I'm told in the information is that the area of the writing is 50 square inches. So area is L times W, which is equal to 50. And this time I will solve this for W and say that W is equal to 50 over L. Then what I know is for the whole poster, my area is the full length, which we said was L plus 8, times the full width, which is W plus 4. I want to make a substitution of 50L for W so that I have this equation just in one variable. So my area is going to be L plus 8 times 50 over L plus 4. And then I want to multiply all of that out and simplify it a little bit. And when I do that, I'm going to end up with 4 L plus 400 over L plus 82. So this is the area that we want to maximize, and therefore we have to take the first derivative. That is, find A prime. That's going to be 4, and here's our famous 1 over L times 400, so it's going to be minus 400 over L squared. And 82, of course, turns out to be 0. We have the first derivative now. A prime is equal to 4 minus 400 over L squared, and we need to set that equal to 0 and solve for L in order to find the minimum amount of paper. So we set it equal to 0, and then we solve for L. When we do that and work it all out, L works out to be equal to 10. Now, if L is equal to 10, we know that we actually have to add 8 to that. So the posters is going to be 18 inches tall. And now in terms of W, remember that W is equal to 50 divided by L, which means the width inside of the writing is 5. And that makes sense because 5 times 10, the length, would give us the 50 inches of writing. But remember that we've got to add 4 to W. So W is 5, but the poster itself is 9 inches wide. So it's 18 inches tall and 9 inches wide. Now we're going to try an example from economics. Suppose that the revenue, R of x, is equal to 9x, represents the revenue, and C of x, which is equal to x cubed minus 6x squared plus 15x, represents cost, with x measured in thousands of units. Is there a production level that maximizes profit? And if so, what is it? Well, maximum profit is going to occur when what's called marginal revenue equals the marginal cost. And recall that marginal in the economics world means the first derivative in the math world. So what we're going to do is take those two functions and find each of their derivatives. The derivative of the revenue and the derivative of the cost. So let's do that. R of x is equal to 9x. And that means that R prime of x is equal to 9. And then we have the cost function, which is equal to x cubed minus 6x squared plus 15x. And we take the derivative of that. C prime of x equals 3x squared minus 12x plus 15. And then we set these two equal to each other. 3x squared minus 12x plus 15 equals 0. Equals 9. And then we want to make the right-hand side equal to 0. So 3x squared minus 12x plus 15 minus 9 is 6. And when you solve this quadratic, it actually does not factor, so you use the quadratic formula, and we will get an answer of 12 plus or minus the square root of 72 all over 6. So that gives us two distinct answers, and we need to look at both, so let's do that. We get x equals 12 plus the square root of 72 over 6. And that's going to be equal to 3.1414 4. And our other answer is when we have a subtraction there, and when we have, so it'd be 12 minus the square root of 72, and in that case we get x is equal to 0.586. So now it's a question of which of these is the min or the max in terms of figuring out maximum profits. So there's two ways we can do this. We can take those critical values, remember that's what those are, and we can plug them back into the original equations, the original formulas, to figure out the numerical value and then determine it. Or we can take a look at the graphs. So let's do that. Here are the graphs for both the revenue function, and the revenue function is 9x, and it's this red line, the straight line. And our cost function is the blue line. So the reason that's important is notice that what's happening is here, where we have maximum profit, you can see that the revenue function is clearly above the cost function. And that's occurring for the point which was simplified to 2 plus radical 2, which is the 3.1414. Whereas over here, when we look at my other answer, which worked out to be 0.586, you can see that the cost function is actually greater than the revenue function. So we're actually losing money there. In fact, that is where we have the maximum loss. So the production level would be 3,414 units, because remember, each of the 3.1414, each one of those represents 1,000 units. Well, now it's time for you to try a problem. Suppose r of x equals 8 times the square root of x represents the revenue, and c of x equals 2x squared represents the cost. With x measured in thousands of units, is there a production level that maximizes profits? And if so, what is it? Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out the value of x that actually maximizes the profit. To do that, it's similar to the example I did for you. We need to find the derivatives of each of those two functions and then set them equal to each other. So let's do that. We have r of x equals 8 square roots of x. And we take the derivative of that, and we end up, remember, this is like x raised to the 1/2 power, so that we take the 1/2, and we can get rid of this. And so we get 4x to the negative 1/2. For the cost function, c of x is 2 times x squared. And so c prime of x equals 4x. We set these equal to each other. 4x to the negative 1/2 equals 4x. And what you should notice in here, although we certainly could go through some steps to solve it, is that x has to be equal to 1. That's the only way that we can have a power of negative 1/2 equaling a understood power of 1. So x equals 1. And so what that means is 1,000 units is the amount that should be produced to maximize the profits. Great job. So in this lesson, we learned about using the first derivative and applying it to minimize and maximize real-world applications. Be sure to work the exercises that your teacher assigns, and we'll see you next time.